Okay, so first we're gonna look at the problem number one. In problem number one, we are given the temperature of a gas stream to be measured by a thermocouple whose junction can be approximated as 1.2 millimeter diameter sphere. So he gave us the diameter of the sphere of the junction. The properties of the junction are K. He gave us the thermal conductivity, the density, and the Cp, which is 320 joule per kilogram Kelvin. The heat transfer coefficient H is 90 watt per meter square Kelvin, and they're asking us to determine how long it will take for the thermocouple to reach 99% of the initial temperature difference. So first of all, we must determine whether we can use the lump system analysis or we cannot. To know this, we must calculate the Bayer number, which is HLC divided by K. And LC is determined by saying that we have a volume that can be divided by the area of the surface. Now the volume is given by pi d cubed over 6, which is and the area of the surface is just 4 pi r square or pi d square, and we get that it's just the diameter of the sphere divided by 6. We're given the diameter of the sphere here to be 1.2 millimeter, which is 0.012 meter. Once we divide it by 6, we get the LC, and we plug it now inside of the Bio number. After you plug it inside of the Bio number, we get the Bio number to be 0.006, which is less than 0.1. Thus, we can use the lump system analysis. The idea is that convection in this and in this analysis can be almost neglected, and we can use this relation that we learned in class to determine the time, which is T minus T infinity over initial temperature minus T infinity is equal. Okay, so to continue, we have T at the time we want minus T infinity over the initial temperature minus T infinity is going to be E minus BT. We didn't learn this B in class, but we learned that we learned the formula with this constant, which is HA divided by density multiplied by Cp multiplied by V. Now, if we divide the area by the volume, we get 1 over LC, which is the term here. And we just plug in the numbers and we get the constant B to be equal to 0.1654 1 over second. And here they're asking us the time for the thermocouple to read 99 of the initial temperature, which means that the ratio should be the ratio of the temperature minus the initial temperature minus the ambient temperature over the initial temperature minus the ambient temperature should be 1 minus this 99% that they gave us, which is 0.01. After we plug in the numbers we get this equation, and after we use len both sides, we get that the time to reach the 99 or for it to reach the 99% of the initial temperature is going to be 27.8 seconds. شباب أسئلة ما أسئلة. This is actually a good question. So for us to be able to solve this problem, this value should be known, T minus T infinity over Ti minus T infinity. So he should at least give us the ambient temperature, which is T infinity, the initial temperature, and the temperature at the time that he wants. But for him to if we want to say like make things easier for him and for us, he didn't give us these three parameters. He only gave us that he wants it to be 99% of the initial temperature.
Yeah.
Okay, so just for you to understand, the lump system analysis is an analysis that focuses that we can take our whole system to be one lump, which means that the dimension of the object that we are studying and the convection that is happening is not as much as the conduction happening. Okay, so let's now look at our bio number. So our bio number is equal to h over k multiplied by l or multiplied by lc, which is the length of our which is the length that is governing the heat transfer. Okay, now if this length is too large, then we cannot consider our whole system to be only one lump. And if h is too large, we can also not consider our system to be a whole lump, because then convection would be dominant over conduction. However, if Ho multiplied by L is a small number and we divide it by K, we get a bio number that is less than 0.1. Okay, and when the bio number is less than 0.1, we are going to use the lump system analysis, which means that because this object is too small, then the only variables that are involved in the analysis is time. So our differential equation will only be in terms of temperature and time. Okay, so temperature depends on the time and not on the location. And we can see this, for example, if we have a plate over here and we have a temperature that only varies with time, this means that the temperature over this whole plate is the same because it is only one lump. However, if we went to our previous chapters, we used to see that temperature was also dependent on x, it could be also dependent on y or z, and that is the case when the bio number is greater than 0.1. Now, in lumped systems, we use the equation that theta over theta initial is going to be equal to E minus BT, and we discussed what this constant B earlier means. Okay, so this means that the difference in temperature depends on time only because B is a constant. However, let me show you this graph over here. This explains how when bio number is greater than 0.1, we need to use these type of graphs. Now, what is this graph? This graph tells you that the amount of heat transfer happening, so for example, Q, divided by Q max, or the initial Q that is happening, so the maximum amount of heat transfer, which you can notice to maximally be only 1 because that is logically the number of this ratio, can be determined from two parameters. The first parameter is your bio number square multiplied by your Fourier number. We already discussed what bio number means, and we know what the Fourier constant means. It's basically just one thing for the conduction heat transfer. So the bio number square multiplied by the Fourier number along with your value for the bio number can give you the value of Q over Qi. And let me give you an example here. So for example, if your bio number was somewhere along 1, okay, and your bio number square multiplied by Fourier number is also 1. So you can go to 1 on the graph, you can go to this curve over here, and you can get the solution to your differential equation through this graph directly. You can take this Q over here, you find out that Q divided by Q initial is equal to 0.55. So in the previous question, what we had that we had an information that gave us all of this, right? We had that the 99% of the initial temperature was red. So this meant that the theta over theta 0 in the lumped system analysis was given directly to be 0.01. However, when the lumped system are not applicable, we can use this graph to directly determine theta over theta 0, as we said before, depending on the bio number and the Fourier number. Okay, does this make sense to you?